Tonight, we're going to confront what might be the most disturbing question in all of science. There are more planets across the cosmos than there are grains of sand on every beach on Earth. Hundreds of billions of worlds orbiting hundreds of billions of stars. Many of them sit at just the right distance for liquid water. Some of them have been sitting there for billions of years longer than Earth has existed. When we point our most sensitive instruments at the sky and listen, we hear nothing. No signals, no beacons, no evidence that anyone, anywhere, has ever built anything we can detect. The silence is total, and the real reason for it is far more unsettling than most people realize. By the end of tonight, you are going to understand why. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Let's begin. Here is a number that would have stunned every astronomer who ever lived before the year 1995. As of mid-2026, NASA has confirmed the existence of more than 6,100 planets orbiting stars other than our own. 6,100 worlds, not hypothetical objects, not theoretical predictions, confirmed, measured, catalogued planets with known masses, known orbits, known distances from their parent stars, and those are only the ones we have confirmed so far. There are more than 8,000 additional candidates still waiting for verification. Objects that look like planets, behave like planets, and almost certainly are planets, but have not yet passed every test required for official confirmation. So the real number is already pushing toward 15,000 known or suspected worlds. And this entire count represents a tiny, almost laughably small sample of what actually exists out there. Before 1995, no one had confirmed a single planet orbiting a normal sun-like star beyond our own. We suspected they were out there. The physics strongly suggested it. Stars form from collapsing clouds of gas and dust, and the leftover material naturally settles into a disk around the new star. Planets form from that disk. It would have been strange if this process happened only once in a galaxy of hundreds of billions of stars. But suspecting something and proving it are different things, and for decades, we could not prove it. Then, in October of 1995, Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a massive planet, roughly half the mass of Jupiter, orbiting a sun-like star about 50 light-years from Earth. It was nothing like anyone expected. It orbited its star in just over 4 days, far closer than Mercury orbits our sun. It was a gas giant practically hugging its parent star, a type of world that no one had predicted, but it was real. And it changed everything. Because if planets existed around other stars, then the question was no longer whether they were out there. The question was how many. The answer came faster than anyone anticipated. In 2009, NASA launched the Kepler Space Telescope. Kepler's mission was straightforward in concept and revolutionary in execution. It stared at a single patch of sky in the constellation Cygnus, monitoring roughly 150,000 stars simultaneously, watching for tiny periodic dips in brightness. When a planet passes in front of its star from our perspective, it blocks a small fraction of the star's light. The amount blocked depends on the planet's size relative to the star. The duration of the dip tells you about the orbit. The frequency of the dip tells you how long the planet takes to go around. It is an elegantly simple method, and Kepler applied it at a scale that had never been attempted before. Over its primary mission, Kepler detected thousands of planets. But the raw detections were only the beginning of what Kepler taught us. Because Kepler was not looking at the entire sky. It was looking at one small patch. And the transit method only works when a planet's orbit happens to be aligned with our line of sight. Most planets do not transit from our perspective. Their orbital plane is tilted relative to us, and they pass above or below their star from our viewpoint, producing no detectable dip. Statistically, only a small percentage of planets will transit. For an Earth-sized planet orbiting a Sun-like star at Earth's distance, the probability is roughly half of 1%. This means that for every planet Kepler actually detected, there were potentially hundreds more in the same field that it could not see because geometry was not in our favor. When astronomers corrected for this, when they took Kepler's detections and extrapolated to account for all the planets that must exist but did not happen to transit, the numbers were staggering. The conclusion was that, on average, every star in the Milky Way has at least one planet. Many stars have multiple planets, and a meaningful fraction of those planets are rocky worlds orbiting within the habitable zone of their star, the range of distances where temperatures could allow liquid water to exist on the surface. Current estimates, drawn from Kepler data and refined by subsequent observations, suggest that roughly 20% of Sun-like stars have at least one rocky planet in the habitable zone. The Milky Way contains somewhere between 100 billion and 400 billion stars. Even using conservative numbers, that translates to billions of potentially habitable rocky worlds in our galaxy alone. Not in the entire universe. In our galaxy. One galaxy among hundreds of billions. Let that settle for a moment. Billions of rocky planets, sitting at the right distance from their star, with conditions that could, in principle, support liquid water. In this one galaxy. After Kepler and NASA launched the Transiting Exoplanet Survey satellite, known as TESS, in 2018, where Kepler stared deeply at one patch of sky, TESS surveys nearly the entire sky, focusing on the nearest and brightest stars. TESS is designed to find planets around our stellar neighbors, stars close enough that follow-up observations with larger telescopes can study the planets in detail. TESS has already identified thousands of planet candidates, many of them smaller rocky worlds in and near the habitable zones of nearby stars. And critically, TESS is finding these planets around the kinds of stars that dominate the galaxy. Red dwarfs. Small, cool, long-lived stars that make up roughly 75% of all stars in the Milky Way. Red dwarfs burn their hydrogen fuel slowly. Some of them will shine for trillions of years, far longer than the current age of the universe, and many of them have planets. The TRAPPIST-1 system, discovered in 2017, remains one of the most remarkable examples. 7 rocky planets orbit a single red dwarf star, roughly 40 light-years from Earth. 3 of those planets sit within or near the habitable zone. 7 worlds around one small star, and TRAPPIST-1 is not unique. It is simply one of the first systems where we had enough observational sensitivity to detect that many small planets around a faint star. The James Webb Space Telescope, launched in late 2021, has added an entirely new dimension to this picture. Webb can do something that Kepler and TESS cannot. It can analyze the atmospheres of exoplanets. When a planet transits its star, a tiny fraction of the starlight passes through the planet's atmosphere before reaching us. Different molecules absorb light at different wavelengths. By measuring which wavelengths are absorbed, Webb can identify what gases are present in the planet's atmosphere. Carbon dioxide, water vapor, methane, ammonia. Webb has already detected carbon dioxide in the atmosphere of a gas giant, the first definitive identification of that molecule in an exoplanet atmosphere. It has studied the atmosphere of K218b, a sub-Neptune world in the habitable zone of its star, finding methane and carbon dioxide, gases that under certain conditions could be associated with biological processes. But here is where we need to be careful. Detecting molecules is not the same as detecting life. Carbon dioxide exists on Venus, which is a hellscape. Methane can be produced by geological processes with no biology involved at all. A 2025 review published in the Proceedings of the National Academy of Sciences assessed Webb's early results and concluded that while the telescope is capable in principle of identifying potential biosignature gases, the reality is far more complex than a simple detection. Interpreting atmospheric spectra requires understanding the full context: the star's activity, the planet's geology, the atmospheric chemistry, and the many non-biological processes that can mimic biological signatures. The authors noted that even with Webb's extraordinary capabilities, characterizing rocky Earth-sized exoplanets around Sun-like stars remains beyond its reach. The signal is simply too small. Webb's best targets for atmospheric characterization are larger sub-Neptune worlds around smaller red dwarf stars, where the signal-to-noise ratio is more favorable. So we know the planets are there. We know many of them are rocky. We know many of them sit in habitable zones. We are beginning to probe their atmospheres. The universe has turned out to be extraordinarily generous with real estate. Whatever you thought the number might be a generation ago, the actual number is almost certainly larger. The raw materials for life, rocky planets with the right temperatures, are everywhere. And now we arrive at the part that changes the entire tone of the conversation. Because despite all of this abundance, despite billions of potentially habitable worlds in this galaxy alone, despite decades of searching with increasingly sophisticated instruments, we have found no evidence whatsoever that anyone else is out there. The search for extraterrestrial intelligence, known as SETI, has been running in various forms since 1960. That year, astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signals that might indicate a technological civilization. He found nothing. But the idea was powerful, and the search continued. Over the following decades, SETI programs expanded enormously. Radio telescopes listened across wider frequency ranges. More stars were surveyed. The sensitivity of the instruments improved by orders of magnitude. The famous WOW signal, detected in 1977 by the Big Ear Radio Telescope in Ohio, remains the closest thing to an unexplained candidate signal in the entire history of SETI. It was a narrowband radio burst that appeared to match the profile of what an artificial transmission might look like. It lasted 72 seconds. It was never detected again despite repeated attempts to observe the same region of sky. After decades of analysis, its origin remains unresolved, but no subsequent observation has confirmed it as anything other than a one-time anomaly. The search has not been limited to radio waves. Optical SETI programs look for brief, intense pulses of laser light that a civilization might use for interstellar communication. Infrared surveys search for the waste heat that a technologically advanced civilization might produce if it were harnessing a significant fraction of its star's energy. Surveys have looked for megastructures, hypothetical constructions like Dyson spheres that would partially or fully enclose a star to capture its energy output. None have been found. In 2020, the Breakthrough Listen project, the most comprehensive SETI program ever undertaken, published results from its survey of more than 1,000 nearby stars. They observed each star across a wide range of radio frequencies, looking for narrowband signals that natural astrophysical processes do not produce. They found nothing that could not be attributed to human-made radio interference or natural phenomena. And then in 2025, a new opportunity appeared. In July of that year, astronomers discovered the third confirmed interstellar object to enter our solar system. They designated it 3I Atlas. It followed Oumuamua, the strange cigar-shaped object detected in 2017, and Borisov, the interstellar comet observed in 2019. 3I Atlas was almost certainly a natural object, a chunk of rock and ice ejected from some distant star system and drifting through the galaxy until it happened to pass through ours. But the SETI Institute recognized an opportunity. If any interstellar visitor were ever going to carry a technological signature, some faint radio emission from an artificial source, this was a chance to look. They pointed the Allen Telescope Array at 3I Atlas and observed it across frequencies from 1 to 9 gigahertz, collecting nearly 74 million individual narrowband signals over more than 7 hours of observation. After extensive filtering to remove terrestrial radio interference, they examined the remaining candidates one by one. They found nothing. No signal worthy of follow-up. The results, published in 2026 in the Astronomical Journal, placed upper limits on the power of any radio transmitter on or near the object, ruling out signals stronger than about 10 to 110 watts across the observed frequency range. 3I Atlas is a natural object, drifting silently through our solar system, carrying no message and no technology from wherever it came. This is the pattern. Every search, every survey, every new instrument, every new method returns the same result. Silence. Not ambiguous silence. Not silence that could be explained by our instruments being slightly too weak, but a deep, consistent, confirmed absence of any detectable signal from any direction at any frequency we have examined. And this is where the real question begins to take shape. Because the silence is not what anyone expected. In 1961, Frank Drake convened a meeting at the Green Bank Observatory in West Virginia. He gathered a small group of scientists, including the astronomer Carl Sagan, to discuss the question of how many detectable civilizations might exist in the galaxy. Drake proposed an equation, now known as the Drake equation, that broke the question into a series of factors. The rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction of those where life arises, the fraction where intelligence evolves, the fraction that develop detectable technology, and the length of time such civilizations remain detectable. At the time, most of those factors were essentially unknown. The fraction of stars with planets was a guess. The probability of life arising was a guess. Everything after that was speculation layered on speculation. But the equation served an important purpose. It showed that even with conservative estimates for most factors, if civilizations lasted for any significant period, the galaxy should contain at least a few of them. What has happened since 1961 is that several of the early factors in the equation have been pinned down by observation, and the results have been overwhelmingly favorable. The fraction of stars with planets is not a small number. It is essentially one. Nearly every star has at least one planet. The number of habitable zone rocky planets per star is not vanishingly small. It is somewhere between 0.1 and zero point 0.4 for sun-like stars, and potentially higher for red dwarfs. The first few terms in the Drake equation are larger than Drake himself estimated. The universe has given us more raw material than the most optimistic predictions of the 1960s suggested. And yet the silence remains total. This is the contradiction at the heart of this entire story. The universe is not stingy with planets. It is overflowing with them. Rocky worlds in habitable zones are not rare exceptions. They are a routine feature of stellar systems across the galaxy. The ingredients for the story of life, the right kind of planet at the right distance from the right kind of star, exist in numbers so large that they resist intuition. Billions in this galaxy, trillions across the observable universe, but nobody has called. The physicist Enrico Fermi is credited with crystallizing this contradiction during a casual lunch conversation at Los Alamos National Laboratory in 1950. The story goes that Fermi and his colleagues were discussing reports of unidentified flying objects, and Fermi suddenly asked a question that has haunted science ever since. Where is everybody? The question was simple. The universe is vast and old. Stars and planets are common. If life arises with any reasonable frequency, and if civilizations develop and survive for any significant time, the galaxy should have been colonized many times over by now. Even at speeds far below the speed of light, a single expanding civilization could spread across the entire Milky Way in a few tens of millions of years. That sounds like a long time, but the galaxy is more than 13 billion years old. There has been plenty of time for someone to show up, and yet, no one has. Fermi's question is not a paradox in the strict logical sense. It is an observation. It is the gap between what we expect based on the numbers and what we actually see when we look. And as the numbers have gotten better, as we have confirmed that planets are everywhere, the gap has only widened. So something in the chain is breaking. Think of it this way. Between a bare, rocky planet sitting in a habitable zone and a civilization capable of sending a signal that we could detect across interstellar distances, there is a long series of steps. Each step has to succeed for the next one to become possible. A planet has to develop the right chemistry. Life has to originate. That life has to become complex. Complex life has to develop intelligence. Intelligence has to build technology. Technology has to produce detectable signals. And the civilization behind those signals has to survive long enough for the signals to reach someone who is listening. If every one of those steps were easy, if each one happened reliably on most habitable planets, then the galaxy should be teeming with signals. We should be swimming in evidence of other civilizations. We are not. The silence tells us that at least one of those steps, possibly several, is either extraordinarily rare, extraordinarily difficult, or extraordinarily brief. The planets are not the bottleneck. We know that now with confidence that would have seemed impossible a generation ago. The bottleneck is somewhere else. Somewhere in the long, fragile chain between a world that could support life and a civilization that can announce its existence to the stars. Something in that chain fails almost every time. And the rest of this story is about figuring out where. Because when you look at that chain closely, when you examine each link with the care that the evidence demands, what you discover is not a single dramatic barrier. It is something more subtle and in many ways more unsettling. It is a series of gates, each one a little harder to pass through than the last, each one filtering out more and more worlds, until the number that make it through the entire sequence is so small that the silence begins to make a terrible kind of sense. The first gate, the one that separates a sterile planet from a living one, is the one we understand least. And it may be the hardest of all. Let us start with the first gate. A rocky planet sits in the habitable zone of its star. It has liquid water on its surface. It has a source of energy, either sunlight or chemical gradients at hydrothermal vents on the ocean floor. It has the basic chemical elements that life as we know it requires: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Everything is in place. The table is set. The raw ingredients are all present. But before we get to that step, we need to pause and ask a more basic question. Is a planet in the habitable zone actually ready for biology? Because sitting at the right distance from a star is necessary, but it is nowhere near sufficient. A planet can orbit at exactly the right distance and still be completely hostile to life, for reasons that have nothing to do with temperature. Start with geology. Earth has plate tectonics. The crust is broken into large plates that move, collide, separate, and subduct beneath one another over hundreds of millions of years. This process does something that is easy to overlook and almost impossible to replace. It recycles carbon. Carbon dioxide is a greenhouse gas. It traps heat in the atmosphere. Over geological time, carbon dioxide is pulled out of the atmosphere by weathering of silicate rocks and dissolved into the ocean, where it is eventually drawn into the mantle at subduction zones. Volcanic activity then returns it to the atmosphere. This creates a thermostat, a long-term feedback loop that has kept Earth's surface temperature within a range compatible with liquid water for billions of years, despite the fact that the sun has grown roughly 30% brighter since the Earth formed. Without plate tectonics, this thermostat does not function. Carbon dioxide either accumulates unchecked, producing a runaway greenhouse like Venus, or is drawn down permanently, leaving the planet frozen. Mars may be an example of the second outcome. It was once warmer and wetter, but it is a small world. Its interior cooled, plate tectonics never developed or stalled early, and the carbon cycle shut down. The atmosphere thinned. The surface froze. Whatever habitability Mars once had was temporary. We do not know how common plate tectonics is on rocky planets. It appears to depend on planet size, composition, internal heat, and the presence of water in the mantle. It is not a guaranteed feature of rocky worlds. It may be relatively unusual, and without it, a planet's habitability has an expiration date measured in hundreds of millions of years, rather than billions. That is not long enough for the chain we are discussing. Complex life on Earth took nearly 4 billion years to develop. A planet that loses its climate stability after 500 million years never gets the chance. Then there is the magnetic field. Earth generates a strong magnetic field through the churning of liquid iron in its outer core. This field extends far into space, creating a magnetosphere that deflects the solar wind, a constant stream of charged particles flowing outward from the sun. Without this shield, the solar wind would gradually strip away the atmosphere. Mars, again, is the cautionary example. It lost its global magnetic field early in its history, and its atmosphere was slowly eroded by the solar wind, until what remains is less than 1% the density of Earth's. A planet without a magnetic field can sit in the habitable zone and still lose the atmosphere it needs to support liquid water and protect surface life from ultraviolet radiation. The moon matters more than most people realize. Earth's moon is unusually large relative to the planet it orbits. It is believed to have formed from a giant impact early in Earth's history, when a Mars-sized body, sometimes called Theia, struck the young Earth and blasted a vast amount of debris into orbit, which coalesced into the moon. This event was not a predictable outcome of planetary formation. It was a specific collision at a specific angle and velocity, and the moon it produced has had a stabilizing effect on Earth's axial tilt. Without the moon, Earth's tilt would vary chaotically over millions of years, swinging from nearly 0 degrees to more than 45 degrees. This would produce wild swings in climate, with some epochs having no seasons at all, and others having extreme seasonal variation that could render large parts of the surface uninhabitable. The moon's gravitational influence keeps Earth's tilt within a narrow range, around 22 to 24.5 degrees, producing the moderate, stable seasons that complex ecosystems depend on. And then there is the gas giant question. Jupiter, sitting in the outer solar system, acts as a partial gravitational shield for the inner planets. Its enormous mass deflects or captures a significant fraction of the comets and asteroids that would otherwise bombard Earth. Without Jupiter, the impact rate on Earth would be substantially higher. Early in Earth's history, heavy bombardment was unavoidable and may even have delivered water and organic molecules. But after life established itself, continued heavy bombardment becomes a threat rather than a benefit. A planet that is struck by a large asteroid every few million years never develops complex life, because the clock keeps getting reset. Jupiter does not eliminate impacts entirely. The Chicxulub asteroid got through, and that impact, as we will discuss, turned out to be crucial for the chain that produced us. But Jupiter reduces the frequency of such events to a level where long stretches of biological development can proceed without interruption. Each of these factors, plate tectonics, a magnetic field, a stabilizing moon, a protective gas giant, is an additional filter. None of them is guaranteed by the mere existence of a rocky planet in a habitable zone. Each one narrows the pool of candidates further. A planet can have the right temperature, the right chemistry, and the right distance from its star, and still fail the test for habitability because its geology, its magnetic properties, its orbital companions, or the circumstances of its formation did not line up in the right way. The chain, in other words, does not begin with life. It begins before life. It begins with the planet itself, and the planet has to pass its own set of filters before biology even has a chance to start. Now life has to begin. This step, the transition from non-living chemistry to the first self-replicating biological system, is called abiogenesis, and it is the most poorly understood step in the entire chain from planet to civilization. We do not know how it happened on Earth. We do not know how likely it is to happen on any given world. We do not know whether it is a process that occurs readily whenever the conditions are right, or whether it is so improbable that it may have happened only once in the entire observable universe. And we are the result. What we do know is this: the Earth formed approximately 4.5 billion years ago. For the first several 100 million years, the Hadean Eon, the surface was a hellscape of molten rock, constant bombardment by asteroids, and temperatures that would have destroyed any complex organic molecules. Conditions stabilized enough for liquid water to persist on the surface roughly 4 billion years ago. And the earliest evidence we have for life on Earth dates to somewhere between 3.7 and 3.9 billion years ago. Possibly earlier, depending on how you interpret certain chemical signatures in ancient rocks. That is a surprisingly narrow window. The planet became habitable, and life appeared within a few 100 million years at most. Some researchers interpret this as evidence that abiogenesis is relatively easy, that whenever conditions permit, life arises quickly. If it happened fast here, the argument goes, it probably happens fast elsewhere too. But this reasoning has a flaw, and it is a serious one. We are reasoning from a sample of one. Earth is the only planet where we know life exists, and our existence here introduces a profound selection bias. We can only observe the planets where life did arise because we are the observers. If abiogenesis is extraordinarily rare, happening on only one planet in a trillion, we would still find ourselves on that one planet, looking at the evidence and concluding that it happened quickly. The speed of abiogenesis on Earth tells us less than we might hope, because we were never going to find ourselves on a planet where it did not happen. In 2025, a study by Robert Endries at Imperial College London brought new mathematical rigor to this question. Endries developed a framework for estimating the probability of spontaneously assembling structured biological information under realistic prebiotic conditions. His conclusion was sobering. The spontaneous origin of life from non-living chemistry faces far greater challenges than many researchers had previously assumed. The difficulty is not just assembling the right molecules, it is assembling them into functional systems, self-replicating molecules capable of carrying and transmitting information under conditions that are chemically plausible for the early Earth. The combinatorial space is vast. The number of possible molecular arrangements that do nothing useful overwhelms the number that do something biologically meaningful by an almost incomprehensible margin. This does not mean abiogenesis is impossible. It happened at least once. We are the proof. But it suggests that the first gate in the chain may be far narrower than optimists have assumed. A universe full of habitable planets does not automatically produce a universe full of living planets if the step from chemistry to biology is genuinely hard. And even if we set abiogenesis aside, even if we assume that simple life arises on every habitable world within a few 100 million years, the chain does not get easier from there. It gets harder. For approximately the first 2 billion years of life on Earth, the only living things were prokaryotes. Simple, single-celled organisms without a defined nucleus. Bacteria and archaea. They are extraordinarily successful in their own right. They colonize every environment on Earth, from boiling hot springs to frozen Antarctic lakes, from deep ocean hydrothermal vents to the insides of rocks kilometers below the surface. Prokaryotic life is tough, adaptable, and persistent, but it is simple. A prokaryote does not think. It does not build. It does not look at the stars and wonder. If the story of life on Earth had ended with prokaryotes, and for 2 billion years it looked like it might, then Earth would be a living world, but not an interesting one from the perspective of anyone hoping to detect a civilization. The transition that changed everything was the evolution of eukaryotic cells. Eukaryotes are fundamentally different from prokaryotes. They are larger, more complex, and they contain specialized internal structures called organelles that perform specific functions. The most important of these is the mitochondrion. the organelle that generates most of the cell's energy. Mitochondria have their own DNA, separate from the cell's nuclear DNA. This is because mitochondria were originally free-living bacteria that were engulfed by a larger cell in an event called endosymbiosis. Two separate organisms merged into one, and the result was a cell with dramatically more energy available to it. This event, the engulfment of one prokaryote by another in a way that produced a stable, heritable partnership, appears to have happened exactly once in the entire history of life on Earth. Every eukaryotic organism alive today, every animal, every plant, every fungus, every protist, descends from that single merger event. It did not happen repeatedly. It did not happen in parallel across different lineages. It happened once, approximately 2 billion years after prokaryotic life first appeared, and it transformed everything that followed. 2 billion years is an extraordinarily long time. It is nearly half the current age of the Earth. If the transition from prokaryote to eukaryote were easy, if it were a natural and likely outcome of prokaryotic evolution, you would expect it to have happened much sooner and much more often. The fact that it took 2 billion years and apparently happened only once suggests that this transition is genuinely difficult. It may require a specific and improbable encounter between specific types of cells under specific conditions. It may be one of the hardest steps in the entire chain, and without eukaryotes, you do not get multicellular life, you do not get animals, you do not get brains, you do not get technology. The entire edifice of complex life on Earth rests on a single event that took 2 billion years to occur, and that may have been profoundly unlikely. The next step in the chain is multicellularity. This is the transition from single-celled organisms to organisms made of many cells working together, with different cells performing different functions. Multicellularity has actually evolved independently several times on Earth, in animals, plants, fungi, and some algae. This suggests it may be a somewhat easier step than the prokaryote to eukaryote transition. When the cellular machinery of eukaryotes is available, the leap to multicellularity seems to follow with some regularity, at least on Earth. But there is an important distinction between simple multicellularity and complex multicellularity. Colonies of cells that stick together are one thing. Organisms with differentiated tissues, specialized organs, nervous systems, and coordinated behavior are something else entirely. The kind of complex multicellularity that leads to animals took a very long time to develop. Eukaryotic cells existed for roughly 1 billion years before the first complex multicellular animals appeared in the fossil record. This period, sometimes called the Boring Billion, was an era when life existed but did not do much that would be visible from space. Single cells, simple colonies, algal mats, and not much else for a geological eternity. The first complex animals appeared during the Ediacaran period, roughly 635 to 540 million years ago. These were soft-bodied organisms, many of them with forms that have no clear analogy to anything alive today. Flat, quilted creatures resting on the seafloor. Frond-like organisms anchored in the sediment. Strange, symmetrical beings whose relationship to later animal life is still debated. The Ediacaran fauna was an experiment in complex multicellular life that largely did not survive into the next period. What came next was the Cambrian explosion, beginning roughly 540 million years ago. In a geologically brief window of perhaps 20 to 25 million years, nearly all the major animal body plans that exist today appeared in the fossil record, eyes, limbs, shells, skeletons, complex nervous systems, predator-prey dynamics. The Cambrian was not a gradual unfolding. It was a burst of innovation so rapid and so dramatic that Darwin himself found it troubling, because it seemed to contradict the slow, steady gradualism he expected from natural selection. Why the Cambrian explosion happened when it did, and not earlier or later, is still debated. Rising oxygen levels in the atmosphere and oceans probably played a role. An arms race between predators and prey may have driven rapid diversification. Changes in ocean chemistry may have enabled the development of hard body parts like shells and exoskeletons. But whatever the cause, the timing matters for our question. Complex animal life did not appear for nearly 4 billion years after Earth formed. That is roughly 87% of Earth's current history spent without anything more complex than single cells and simple colonies. And once complex animal life did appear, there was no guarantee it would produce intelligence. This is a point that seems counterintuitive, because we tend to think of evolution as a process that trends upward toward greater complexity and greater cognitive ability. It does not. Evolution trends toward reproductive fitness, which is a very different thing. Intelligence is one strategy for achieving reproductive fitness. It is not the only strategy, and it is not even a particularly common one. Consider insects. They appeared roughly 400 million years ago, within 100 million years of the Cambrian explosion, and they have been spectacularly successful ever since. There are more species of beetle alone than there are species of mammal, bird, reptile, and amphibian combined. Insects have colonized virtually every terrestrial environment on Earth. They have survived every mass extinction event. By any measure of evolutionary success, durability, diversity, sheer biomass, insects are among the most dominant life forms this planet has ever produced. And in nearly 500 million years, no insect lineage has developed anything approaching human-level cognition. They did not need to. Their strategy, small bodies, rapid reproduction, specialized behavior, exoskeletons, flight was more than sufficient. Intelligence was simply not what the environment was selecting for. The same is true of fish, which have existed for over 500 million years, and of mollusks, which include the cephalopods, the most cognitively sophisticated invertebrates, capable of problem-solving, tool use, and complex behavior, yet which have never developed language or cumulative culture. It is true of sharks, which have persisted for over 450 million years with barely any change to their basic body plan, because the plan works. Evolution does not push life toward bigger brains. It pushes life toward whatever works, and in most environments, for most lineages, what works is something other than intelligence. Large brains are expensive. The human brain accounts for roughly 2% of body mass, but consumes approximately 20% of the body's energy. That is an enormous metabolic investment. For such an investment to be favored by natural selection, the environment has to present challenges where cognitive flexibility provides a significant reproductive advantage over simpler, cheaper strategies. That combination of pressures, social complexity, variable environments, the need for cooperation and planning, does not arise for every lineage in every environment. It arose for one lineage of African primates under one particular set of ecological and social conditions. And even within that lineage, it took millions of years of additional selection to produce the level of cognition that enables abstract thought and language. On a planet with a rich biosphere, teeming with complex multicellular life, evolution could run for billions of years and never produce a species with the cognitive capacity to build a radio telescope. Not because evolution failed, but because intelligence was never its destination. It was a side path, taken by one lineage, under one set of pressures, and it is not the path that most of life follows. If you were an alien astronomer observing Earth from across the galaxy at almost any point in its history, you would see a living world, but not an interesting one. For most of Earth's existence, there was nothing here that would produce a signal you could detect. Now, let us consider what happened after complex animal life appeared. Because this is where the chain becomes not just difficult, but deeply contingent. Contingent means dependent on specific events that did not have to happen the way they did. Even granting that intelligence is rare as an evolutionary strategy, the particular intelligence that arose on Earth required a sequence of accidents that no one could have predicted. The branch that produced us was not just unlikely in general. It was shaped by specific events that could easily have gone differently. Consider the most dramatic example. 66 million years ago, an asteroid roughly 10 kilometers across struck what is now the Yucatan Peninsula of Mexico. The impact site is called Chicxulub. The energy released was equivalent to roughly 10 billion nuclear weapons detonating simultaneously. It triggered massive wildfires, a global cloud of debris that blocked sunlight for months, acid rain, and a collapse of photosynthesis-based food chains across the planet. Roughly 75% of all species on Earth went extinct, including every non-avian dinosaur. The dinosaurs had dominated terrestrial ecosystems for over 160 million years. They were spectacularly successful. Some were enormous, some were fast. Some may have been quite intelligent by reptilian standards, but in 160 million years of dominance, no dinosaur lineage developed anything resembling technology or language or civilization. Intelligence of the kind that builds radio telescopes is not what evolution was selecting for in the Mesozoic. Speed, size, strength, sensory acuity, these were the traits that mattered. The dinosaurs were exquisitely adapted to their world, but adaptation to a world is not the same thing as developing the capacity to understand it. When the asteroid struck and the dinosaurs vanished, it opened ecological niches that small, nocturnal mammals had been quietly occupying for tens of millions of years. Freed from the pressure of dinosaur competition, mammals diversified rapidly. Over the next 66 million years, they filled the roles the dinosaurs had left vacant. Some became large herbivores, some became predators, some took to the oceans, some took to the air. And one lineage, the primates, developed large brains, social complexity, and eventually the capacity for language, abstract thought, and technology. But if that asteroid had missed, if it had arrived 10 minutes earlier or later and sailed past Earth into empty space, the dinosaurs would almost certainly still be here. Mammals would still be small, nocturnal creatures hiding in the underbrush. There would be no primates, no humans, no radio telescopes, no one to ask where everybody is. The Earth would still be a living world, teeming with biodiversity, but it would have produced no technological civilization. Not because life failed, but because the specific contingent event that opened the door to mammalian dominance never happened. This is not a minor detail. This is the kind of thing that determines whether a living world produces a civilization or remains biologically rich but technologically silent for billions of years. And even after intelligence evolves, the chain is still not complete. Because intelligence alone does not produce technology. This is a point that deserves more weight than it usually receives. Anatomically modern humans, Homo sapiens, have existed for roughly 300,000 years. Our brains reached their current size and structure long before the first city was built, long before the first written word was recorded, long before anyone smelted metal or calculated an orbit. For the vast majority of our existence as a species, we lived as hunter-gatherers in small nomadic bands. We had language, we had complex social structures, we had art, ritual, and culture. We were, by any reasonable measure, intelligent, but we did not have technology in the sense that matters for this question. We did not have agriculture, writing, metallurgy, mathematics, or any of the accumulating systems of knowledge that eventually led to science and engineering. For more than 290,000 of our 300,000 years as a species, we were intelligent beings who produced no signal that anyone beyond our atmosphere could have detected. What changed? The end of the last ice age, roughly 11,700 years ago, created conditions in certain regions, particularly the Fertile Crescent of the Middle East, where wild grains and animals suitable for domestication existed in proximity to human populations living in relatively stable environments. Agriculture emerged, not because humans suddenly became smarter, but because environmental conditions aligned in a way that made farming possible and advantageous. Agriculture produced surplus food. Surplus allowed population growth and the division of labor. Division of labor enabled specialization. Specialization produced craftspeople, builders, administrators, and eventually scholars. Writing emerged to manage the complexity of agricultural societies. Mathematics emerged to solve practical problems of measurement, trade, and construction. Over thousands of years, these accumulating systems of knowledge built upon each other until they produced science, the systematic investigation of nature and then technology, the application of scientific understanding to build things that nature does not provide. This entire sequence, from the end of the Ice Age to the first radio transmission, took roughly 11,500 years, and it depended on specific conditions that were not inevitable. If the last Ice Age had not ended when it did, or if the particular constellation of domesticable plants and animals had not existed in the regions where human populations were concentrated, the agricultural revolution might have been delayed by thousands of years, or might not have happened at all in the form it took. We know that anatomically, modern humans lived in Australia for roughly 65,000 years without developing agriculture independently, not because they were less intelligent, but because the Australian continent lacked the suite of easily domesticable grain crops and large mammals that enabled agriculture in the Fertile Crescent. Technology, in other words, is not a biological inevitability. It is a cultural and environmental outcome that requires intelligence, yes, but also requires a specific set of material conditions that allow intelligence to accumulate knowledge across generations in ways that eventually produce science. A planet that produces intelligent beings but lacks the right environmental triggers, the right combination of domesticable species, the right climate transitions, the right geological resources, could remain home to a thriving population of smart, social, linguistically sophisticated creatures who never develop anything recognizable as technology. This is another gate in the chain, and it is one that is easy to overlook because we tend to treat intelligence and technology as though they are the same thing. They are not. Intelligence is a biological trait that evolves under specific selective pressures. Technology is a cultural product that emerges under specific environmental conditions. The first does not guarantee the second. On Earth, the gap between the two was 300,000 years. On another world, with different environmental circumstances, the gap could be permanent. In 2025, a study published in Science Advances by Daniel Mills and colleagues at Penn State and other institutions critically re-examined the hard steps model of evolutionary transitions. The hard steps model, originally proposed by the physicist Brandon Carter in 1983, argues that several key transitions in the history of life were so improbable that they are unlikely to be repeated on other worlds within the habitable lifetime of a typical planet. Carter's analysis suggested that humanity's evolution was intrinsically unlikely and that comparable observers elsewhere should be exceedingly rare. Mills and colleagues did not reject the framework entirely, but they challenged a core assumption. They argued that Earth's environment was not uniformly hospitable throughout its history. Key evolutionary transitions did not simply occur whenever enough time had passed. They became possible only when the global environment reached specific, permissive states. For example, the rise of atmospheric oxygen, which was necessary for complex animal life, was not a steady process. It occurred in at least two major events: the Great Oxidation Event roughly 2.4 billion years ago, and the Neoproterozoic Oxygenation Event roughly 600 to 800 million years ago. Before these events, the oxygen levels in Earth's atmosphere were too low to support large, active, multicellular organisms, regardless of how much time had passed. This matters because it means the timeline on Earth may not generalize to other planets in the way Carter assumed. If a planet's environment reaches the necessary permissive states earlier, transitions could happen earlier. If it never reaches them, transitions may never happen at all, regardless of how many billions of years are available. The hard steps model, in this revised view, is not just about probability per unit time. It is about the interplay between biological potential and environmental readiness. And that interplay is specific to each planet's unique geological and atmospheric history. The implication is nuanced. On one hand, it suggests that the timing of evolutionary transitions on Earth may not represent a universal speed limit. Complex life could arise faster on a planet with a different geochemistry. On the other hand, it adds another layer of conditionality to the chain. It is not enough for a planet to be habitable. The planet's geology, atmosphere, and chemistry have to evolve in specific ways at specific times to enable each subsequent biological transition. The chain is not just biologically fragile, it is geologically fragile as well. Now step back and look at the full sequence from the perspective of the question we started with. A rocky planet forms in the habitable zone. That happens routinely. We know this from observation. Life has to originate from non-living chemistry. We do not know how likely this is, but recent work suggests it may be genuinely difficult. Simple life has to give rise to complex eukaryotic cells. On Earth, this took 2 billion years and apparently happened exactly once. Complex cells have to produce complex multicellular organisms. On Earth, this took roughly another billion years. Complex organisms have to develop nervous systems, intelligence, and eventually the kind of cognitive capacity that enables language, abstract thought, and tool use. On Earth, this required specific contingent events, including a mass extinction caused by an asteroid impact that could easily have not occurred. And each of these steps has to succeed in sequence. A failure at any point terminates the chain. A planet where life never arises stays sterile. A planet where life stays prokaryotic for its entire history produces no civilization. A planet where complex life evolves but intelligence never emerges produces a rich biosphere but no technology. A planet where an intelligent species evolves but never develops science and engineering produces thinkers but no signals. The critical insight is this: when you multiply low probabilities together, the result drops fast. If each of 5 steps has even a 10% chance of succeeding, the probability of all 5 completing in sequence is not 50% or even 10%. It is 1,000th of 1%, 1 in 100,000. And if each step is even less likely than 10%, which the evidence increasingly suggests for some of them, the final probability drops to numbers that are difficult to distinguish from 0 across any reasonable sample of planets. This is the mathematical heart of why billions of planets can coexist with total silence. It is not that any single step is impossible. It is that the full chain is long, and the cumulative probability of completing it is very, very small. The universe is not stingy with the first ingredient. Planets are everywhere. But the recipe has many steps, and each one filters out the vast majority of worlds that began with all the right raw materials. There is a concept that captures this logic precisely. The economist Robin Hanson called it the Great Filter. The idea is simple. Between a dead planet and a galaxy-spanning civilization, there must be at least one step that is so difficult, so improbable, that it filters out nearly everything that attempts it. The Great Filter might be one single catastrophically hard step, like abiogenesis or the prokaryote to eukaryote transition. Or it might be the cumulative effect of many modestly hard steps. None of them impossible on their own, but collectively forming a barrier that almost nothing passes through. The evidence from Earth's own history is consistent with the second interpretation. There is no single obvious point where life almost failed and barely scraped through. Instead, there is a long sequence of transitions, each of which took an enormous amount of time, each of which may have required specific and unlikely conditions, and each of which had to succeed before the next could begin. The filter is not a wall, it is a sieve with many layers, and each layer catches most of what passes through the one above it. What emerges from this picture is a distinction that matters enormously for the question of whether we are alone. Microbial life and technological civilization are not the same thing. They are separated by billions of years of contingent evolution and multiple low probability transitions. A universe that produces simple life on millions of planets could still produce technological civilizations on almost none of them. The abundance of habitable worlds does not translate into an abundance of civilizations, because the chain between the two is long and fragile and breaks almost everywhere it is attempted. And even this is not the end of the story. Because even if a civilization does complete the entire chain, even if it beats every biological and geological filter and builds the technology to send a signal across the stars, it still has to solve one more problem. It has to last long enough for that signal to matter. It has to survive. And that is where the next set of filters begins. Imagine that every biological filter has been passed. Against enormous odds, a planet has managed the entire sequence. Chemistry became biology. Simple cells became complex cells. Complex cells built bodies, bodies developed brains. Brains grew large and sophisticated enough to support language, abstract reasoning, and cumulative culture. A species emerged that could study the world, develop mathematics, harness energy, and build instruments capable of sending and receiving signals across interstellar distances. This has happened at least once. We are the proof. But completing the biological chain is not the end of the problem. It is, in a sense, where a new and equally unforgiving set of problems begins. Because a civilization that builds a radio transmitter today can go silent tomorrow. And in cosmic terms, tomorrow might as well be the same instant as today. The Drake equation has 7 factors. The first several, the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, have been constrained by observation to values that are encouragingly large. The middle factors, the probability of life, the probability of intelligence, the probability of technology, remain uncertain but are at least grounded in what we know about Earth's history. It is the final factor that dominates everything. That final factor is designated L. It represents the average length of time a technological civilization remains detectable, and it is the single most important variable in the entire equation, because it determines not how many civilizations have ever existed, but how many exist right now, at this moment, producing signals we could potentially receive. Here is why L matters so much. Suppose every other factor in the Drake equation is optimistic. Suppose life arises on most habitable worlds. Suppose intelligence evolves frequently. Suppose technology is a common outcome. If all of that is true, but the average civilization lasts only a few hundred years before going silent, then the number of civilizations detectable at any given time drops to nearly 0. The galaxy could have produced millions of civilizations across its history, and almost all of them could be gone, their signals long since faded, their transmitters long since shut down, their species long since extinct or transformed into something unrecognizable. The mathematics are straightforward and brutal. The Milky Way is approximately 13.6 billion years old. If a civilization arises, broadcasts for 1,000 years, and then goes silent, that 1,000-year window occupies less than 1/10,000,000th of the galaxy's history. For 2 such civilizations to overlap in time, both of them need to be broadcasting during the same tiny sliver of cosmic history. The probability of that overlap depends entirely on how many civilizations exist and how long each one lasts. If civilizations are rare and short-lived, the probability of temporal overlap approaches 0, even in a galaxy with billions of habitable planets. Think about what this means concretely. Suppose a civilization arose on a planet orbiting a star on the other side of the Milky Way 5 billion years ago. They developed radio technology, broadcast signals for 10,000 years, and then went extinct. Their signals traveled outward at the speed of light, expanding in a sphere through the galaxy. But those signals passed through our region of space long before the Earth even formed. By the time our solar system coalesced from its cloud of gas and dust, those signals were already billions of light years away, far beyond the Milky Way, diluted to nothing in the background noise of the cosmos. That civilization existed. It was real. It may have been brilliant, curious, and creative, but we will never know about it, because its window of detectability and our window of listening did not overlap. Now multiply this by every civilization that may have ever arisen in the galaxy, each one occupying its own brief window, each one broadcasting into a cosmos that does not pause to wait for someone to be listening. each one potentially separated from the next, not just by distance, but by millions or billions of years of time. The galaxy could be littered with the archaeological remains of extinct civilizations, silent ruins on 1,000 worlds, and we would have no way to know from here. Dead civilizations do not transmit. So how long does a civilization actually last? This is the question that the Drake equation cannot answer on its own, because we have exactly one example to work from, and our example is not yet finished. Human civilization has existed in its current technological form for a vanishingly brief period. We've been capable of producing detectable radio signals for roughly 100 years. We have been deliberately searching for signals from other civilizations for roughly 65 years. In cosmic terms, this is nothing. It is a single heartbeat in a life measured in billions of years, and we have no guarantee that our own window will remain open. There are many ways a technological civilization can go silent, and not all of them involve dramatic extinction. The most obvious risk is self-destruction. A civilization that develops nuclear weapons, as we did in 1945, acquires the ability to end itself. During the Cold War, the United States and the Soviet Union maintained nuclear arsenals large enough to kill most of the human population and render large parts of the planet uninhabitable. The closest we came to using them in full, the Cuban Missile Crisis of 1962, was resolved partly by luck. Individual decisions made by individual people on both sides, any of which could have gone differently, prevented a nuclear exchange that would have altered the trajectory of human civilization permanently. Nuclear weapons are not the only existential risk. Climate destabilization, if it proceeds far enough, could collapse the agricultural systems that sustain large populations. A sufficiently severe pandemic, naturally occurring or engineered, could devastate a civilization's capacity to maintain complex technology. Resource depletion, the exhaustion of easily accessible energy sources and raw materials, could force a technological regression that takes centuries to reverse, if it can be reversed at all. And there are risks we may not yet have imagined, technologies we have not yet developed, that could prove as dangerous as nuclear weapons in ways we cannot currently foresee. And these are not purely hypothetical risks. Civilizational collapse is not a thought experiment. It is a recurring feature of human history. And the most instructive example may be the one that most closely resembles what we are worried about on a cosmic scale. Around 1200 BCE, the Eastern Mediterranean was home to a network of interconnected civilizations. The Egyptians, the Hittites, centered in what is now Turkey, the Mycenaean Greeks, the city-states of the Levant, including the prosperous trading port of Ugarit, and the great powers of Mesopotamia. These were not isolated societies. They were linked by extensive trade routes, diplomatic correspondence, and mutual dependence. Bronze, the defining technology of the age, required tin and copper, which had to be sourced from different regions and transported across hundreds of miles. The system worked because the network held, and then, within a span of roughly 50 years, the network collapsed. The Hittite Empire fell. Its capital, Hattusa, was burned and abandoned. The Mycenaean palace centers in Greece were destroyed or deserted. Ugarit was sacked and never rebuilt. Egypt survived but was severely weakened, losing control of its foreign territories and entering a long period of decline. Across the region, writing systems fell out of use. Long-distance trade routes broke down, populations declined, Entire cities were abandoned. What followed was a period that historians sometimes call the Greek Dark Ages, lasting roughly 300 years, during which literacy, monumental architecture, and centralized administration largely vanished from the Aegean world. The causes of the Late Bronze Age collapse are still debated. It was probably not a single event, but a cascade. Climate change, producing drought and famine, disruption of trade routes, internal social instability, attacks by groups the Egyptian records call the Sea Peoples, whose identity and origins remain uncertain. What is clear is that the collapse was systemic. It was not one kingdom falling while the others carried on. It was an interconnected network of civilizations failing together because their interdependence, the very thing that made them powerful, also made them fragile. When one critical link broke, the stress cascaded through the system. The result was not extinction. People survived, communities persisted, but the technological and institutional capabilities of the collapsed civilizations were lost for centuries. Writing disappeared from Greece for roughly 400 years. The ability to build monumental stone structures vanished. The administrative systems that had coordinated agriculture, trade, and defense across large regions ceased to function. When civilization re-emerged in the Aegean, it did so from scratch, reinventing writing, reinventing governance, rebuilding trade networks from the ground up. This matters for our question because it demonstrates something that abstract discussions of existential risk often miss. Technological civilization is not a ratchet that only turns in one direction. It can reverse. Complex societies can lose capabilities and not regain them for generations. The knowledge required to maintain advanced technology is not stored in the genes of the population. It is stored in institutions, in training systems, in supply chains, in the accumulated infrastructure of a functioning society. Disrupt those systems badly enough, and the knowledge is lost, even though the people who once possessed it are still alive. Now extrapolate this to a planetary scale. A technological civilization that has been broadcasting radio signals for a few centuries suffers a systemic collapse. Not extinction, but a collapse severe enough to disrupt the energy systems, manufacturing chains, and institutional knowledge required to maintain radio technology. The transmitters go silent. The civilization survives in some form, but it is no longer detectable from interstellar distances. It has, in effect, passed through a filter. Not the filter of extinction, but the filter of regression. And if recovering from that regression takes centuries, or if a second collapse occurs before recovery is complete, the civilization may never regain its detectable phase. Its window of visibility, already narrow, closes permanently. The L variable in the Drake equation does not measure how long a species survives. It measures how long a species remains detectable. And history tells us that these are very different numbers. But extinction is not the only way a civilization goes silent. A civilization could survive and simply stop being detectable. Consider the trajectory of our own communications technology. In the mid-20th century, Earth was a relatively bright radio source. Powerful television and radar transmitters broadcast signals omnidirectionally into space. These signals were not intended for interstellar communication, but they leaked outward at the speed of light, forming an expanding bubble of unintentional radio emission. An alien civilization with a sufficiently sensitive receiver, pointed at Earth at the right frequency, could, in principle, have detected these signals from several light years away. But our technology has changed. We have shifted increasingly from powerful omnidirectional broadcasts to weaker, more targeted communications. Cable television replaced broadcast television. Fiber optic networks replaced radio links. Satellite communications use tightly focused beams aimed at specific receivers, not broad signals sprayed into space. Digital compression and encryption make our signals look more like noise to anyone who does not know the encoding. The unintentional radio leakage from Earth is declining. Within a few decades, our planet may become significantly harder to detect from interstellar distances, not because we have gone extinct, but because our technology has become more efficient and more quiet. If this pattern is typical, if civilizations tend to move from loud, omnidirectional communication to quiet, targeted communication as their technology matures, then the detectable window may be astonishingly brief. A civilization might be radio bright for only a century or two before it transitions to communication methods that are effectively invisible at interstellar distances. The window between developing radio technology and becoming radio quiet might be the narrowest part of the entire chain. It is worth noting that the search for evidence of other civilizations is not limited to eavesdropping on their communications. Scientists have proposed a broader category of evidence called technosignatures. Any observable effect that a technological civilization might produce, intentionally or not, that could be distinguished from natural phenomena at interstellar distances. Some of these ideas are ambitious. In 1960, the physicist Freeman Dyson proposed that a sufficiently advanced civilization might construct a vast swarm of structures orbiting its star to capture a significant fraction of the star's energy output. Such a structure, now called a Dyson swarm, would not be visible in ordinary light in the way a star is, but it would radiate enormous amounts of waste heat in the infrared. A star that appeared unusually dim in visible light, but unusually bright in infrared could, in principle, be a candidate. Surveys have searched for this infrared signature among hundreds of thousands of stars. No convincing candidates have been identified. Other technosignatures are more subtle. A civilization that industrializes might release gases into its planet's atmosphere that do not occur naturally. On Earth, chlorofluorocarbons, the industrial chemicals that damaged our ozone layer, have no known natural source. If a telescope like Webb detected chlorofluorocarbons in the atmosphere of a rocky exoplanet, it would be difficult to explain without invoking industrial activity. In principle, this is within the reach of next-generation telescopes, though it would require stacking observations over hundreds of hours, and the signal would be at the very edge of detectability. Artificial illumination on the night side of a planet is another theoretical technosignature. A civilization that lights its cities would alter the spectrum of light reflected from its planet in ways that differ from natural surfaces. This effect would be extraordinarily faint at interstellar distances, but it has been discussed as a target for future extremely large telescopes. The important point about all of these expanded search strategies is that they face the same fundamental constraints we have already discussed. A Dyson swarm is only detectable if it exists right now, around a star we happen to be observing, and has been in place long enough for its infrared signature to be unambiguous. Industrial pollutants in an exoplanet atmosphere are only detectable if the civilization is actively polluting at the moment we observe, and if the star and planet geometry allows transit spectroscopy. Night-side illumination is only visible if the civilization exists today, and uses lighting technology that alters the planetary spectrum in ways we can measure. Every proposed techno-signature, no matter how creative, runs into the same wall. The civilization has to exist now. It has to be close enough to observe, and it has to be producing the signature at a level our instruments can detect. The filters of time, distance, and signal strength apply to every method, not just radio. Expanding the search to new types of evidence is valuable and necessary, but it does not escape the fundamental geometry of the problem. There is also the possibility of deliberate silence. Some thinkers have proposed what is sometimes called the dark forest hypothesis. The idea that civilizations may choose not to broadcast their existence because doing so is dangerous. If the galaxy contains predatory or aggressive civilizations, announcing your presence and location could invite destruction. A rational civilization, aware of this risk, might maintain strict radio silence, listening but never transmitting, hiding in the darkness like a hunter in a forest. This is speculative, and we have no evidence for or against it, but it illustrates a broader point. We tend to assume that a civilization that develops technology will naturally want to communicate with the cosmos. But that assumption may reflect our own cultural moment more than any universal truth. A civilization might develop technology and then decide, for any number of reasons, that interstellar communication is not worth the cost, the risk, or the effort. They might turn inward, focusing on their own world, their own problems, their own culture. They might lose interest in the stars. Silence does not require extinction. It only requires a decision or a drift toward quietness. Now, let us add distance to the problem, because distance imposes constraints that most people severely underestimate. The Milky Way is approximately 100,000 light-years across. A signal transmitted from one side of the galaxy takes 100,000 years to reach the other side. If a civilization began broadcasting from a star 40,000 light-years away, we would not receive their signal for 40,000 years. And by the time we did, the civilization might have been gone for 39,000 of those years. The signal would be a ghost, an echo of a society that no longer exists, arriving long after anyone was alive to care about a response. Even within our local neighborhood of the galaxy, distances impose severe limitations. The nearest star system, Alpha Centauri, is roughly 4.3 light-years away. A signal sent from there reaches us in about 4 years. That is manageable. But the nearest star with a confirmed potentially habitable planet, Proxima Centauri b, orbits a red dwarf star that is violently active, producing flares that may strip away any atmosphere. The next candidates are farther: 10 light-years, 20, 50, 100. At 100 light-years, a round-trip communication takes 2 centuries. A question sent today receives an answer in the year 2226. The people who sent the question are long dead. The society that sent it may have transformed beyond recognition. This is not conversation. It is an exchange of messages between strangers separated by lifetimes. And 100 light-years is still a tiny distance in galactic terms. It encompasses only a few thousand stars out of hundreds of billions. To survey a meaningful fraction of the galaxy, you need to reach thousands, tens of thousands, hundreds of thousands of light-years. At those distances, communication becomes not difficult, but effectively impossible in any interactive sense. You can transmit, but you will never hear back. Not in your lifetime, not in your civilization's lifetime, if civilizations are short-lived. Signal strength compounds the problem. Radio signals like all electromagnetic radiation, obey the inverse square law. The power of a signal decreases with the square of the distance from the source. Double the distance and the signal becomes 4 times weaker. 10 times the distance and it is 100 times weaker. At interstellar distances, even powerful signals become extraordinarily faint. Earth's most powerful deliberate interstellar transmission was the Arecibo message, sent in 1974 from the Arecibo radio telescope in Puerto Rico toward the globular cluster Messier 13, roughly 25,000 light-years away. It was a narrow beam at a frequency of 2,380 megahertz, carrying a simple encoded message about human biology and our solar system. The transmission lasted less than 3 minutes. To detect this signal at the distance of Messier 13, a receiving civilization would need an antenna comparable in size to Arecibo itself, pointed at exactly the right spot in the sky, tuned to exactly the right frequency, at exactly the right time. The probability of all those conditions being met by chance is vanishingly small. Our unintentional radio leakage is far weaker. The expanding bubble of television and radar signals that has been traveling outward from Earth since the 1930s is now roughly 100 light-years in radius. But these signals were not designed for interstellar communication. They were designed to reach antennas on Earth's surface, a few hundred kilometers away at most. At interstellar distances, they are faint, almost beyond detection. A civilization at the distance of even the nearest stars would need an extraordinarily sensitive receiver to pick them out of the background noise. At 50 or 100 light-years, they would be effectively undetectable with any technology we can currently envision. So, the detectability window is not just about how long a civilization broadcasts. It is about how far those broadcasts reach at detectable strength. A civilization that broadcasts for 1,000 years creates a shell of signals 1,000 light-years thick, expanding outward at the speed of light. But the signals at the outer edge of that shell are the weakest, because they have traveled the farthest. The volume of space within which the signals are strong enough to actually detect is much smaller than the volume of space the signals have technically reached. The effective detectable range depends on the power of the transmitter, the sensitivity of the receiver, the frequency, the bandwidth, the directionality of the transmission, and the background noise environment. For most realistic scenarios, the effective range is measured in tens or hundreds of light-years, not thousands. This means that even a civilization that is actively broadcasting right now, at this moment, could be invisible to us simply because it is too far away. Its signals exist, traveling through space, carrying information about its existence. But by the time they reach us, if they ever do, they are too weak to distinguish from the natural radio emission of the galaxy. The civilization is there. It is broadcasting, and we cannot hear it. Now combine all 3 constraints. A civilization has to exist at the same time as us. It has to be close enough for its signals to reach us at detectable strength. And it has to be actively transmitting in a way that we can recognize. Time, distance, and signal strength. 3 independent filters, each one narrowing the field of potential contacts dramatically. The temporal filter eliminates civilizations that arose too early or too late. Civilizations separated from us by millions or billions of years. The distance filter eliminates civilizations that are too far away. Civilizations whose signals cannot bridge the gap between their star and ours with enough strength to be noticed. The detectability filter eliminates civilizations that are broadcasting in ways we are not equipped to detect, at frequencies we are not monitoring, in modes we do not recognize, or at power levels below our sensitivity threshold. Each of these filters operates independently of the biological filters we discussed earlier. A civilization that passes every biological filter, that completes the entire chain from chemistry to technology, can still be rendered invisible by time, distance, or signal characteristics. The chain does not end when you build a transmitter. It extends all the way to the moment a signal arrives at a receiver operated by someone who recognizes it for what it is. There is one more dimension to the timing problem that deserves attention, because it reveals just how narrow the window of mutual detectability really is. Consider two civilizations in the Milky Way. Call them Civilization A and Civilization B. They are separated by 10,000 light years. Civilization A develops radio technology and begins broadcasting. 10,000 years later, the first signals from Civilization A arrive at Civilization B's star, but Civilization B has not evolved yet. Their planet is still in the equivalent of the Cambrian period, crawling with complex life but no intelligence, no technology, no one to receive a message. The signals from Civilization A wash over their planet, unheard, and continue outward into the void. 3 billion years later, Civilization B finally evolves, develops technology, and begins listening. They point their receivers at Civilization A's star, but Civilization A has been gone for 2.9 billion years. Their planet is still there, orbiting its star, but the civilization is extinct. No signals are being transmitted. Civilization B hears nothing and concludes, as we have, that the galaxy appears to be empty. Both civilizations existed. Both were real. Both asked the same question. And neither ever knew about the other because 10,000 light years of distance and 3 billion years of temporal separation made contact impossible. They were ships passing in the night of cosmic time, separated not by malice or by physics that forbids contact in principle, but by the sheer scale of time and space in which their brief existences were embedded. Now, consider how many such pairs might have existed across the history of the Milky Way. If civilizations are rare and short-lived, the number of pairs that actually overlap in time and space, close enough and simultaneous enough for mutual detection, could be zero. Not approximately zero. Exactly zero. Not because the galaxy never produced civilizations, but because it never produced two of them at the same time and in the same neighborhood. This is the deepest version of the silence. It is not that no one is there. It is that no one is there right now, close enough, broadcasting in a way we can detect. The universe could be full of life, scattered across billions of years and billions of light years, and still present to us as a perfect, unbroken silence. The silence is not necessarily a statement about the emptiness of the cosmos. It may be a statement about the loneliness of time. And there is a cruel asymmetry built into this situation. The silence tells us that either civilizations are extremely rare, or they are extremely short-lived, or they are extremely far apart, or some combination of all three. But it does not tell us which. The observational result is the same in every case. Silence. We cannot distinguish between a galaxy that has never produced another civilization and a galaxy that has produced millions of them, all separated from each other by unbridgeable gulfs of time and distance. The silence is compatible with both extremes and everything in between. This is what makes the Fermi question so difficult to resolve. It is not that we lack data about planets. We have excellent data about planets. It is not that we lack data about stars. We have extraordinary data about stars. What we lack is data about the later stages of the chain. We do not know how often life arises. We do not know how often intelligence evolves. We do not know how long civilizations last. And we do not know how detectable they are. The factors that matter most are the ones we understand least. What we can say, with increasing confidence as SETI surveys grow more comprehensive and continue to return null results, is that the combination of all these factors produces a very quiet galaxy. Whatever the individual probabilities are, their product is small enough that we have detected nothing in over 6 decades of searching. This does not prove we are alone. Absence of evidence is not evidence of absence, particularly when our searches have covered only a tiny fraction of the possible parameter space. We have examined only a small number of stars at a limited range of frequencies with limited sensitivity for a brief period of time. The haystack is enormous, and we have examined only a handful of straws. But the growing sophistication and scale of SETI searches, combined with the continued null result, does constrain the possibilities. It makes certain optimistic scenarios less plausible. If the galaxy contained thousands of civilizations broadcasting powerful omnidirectional radio signals, we would almost certainly have detected something by now. We have not. So either civilizations are rarer than that, or they are quieter than that, or they are briefer than that, or some combination. The Breakthrough Listen project, which began in 2015 with $100 million in funding, represents the most systematic search ever undertaken. It has surveyed over 1,000 nearby stars, the entire plane of the Milky Way, and 100 nearby galaxies at frequencies from 1 to 12 GHz, with sensitivity sufficient to detect a transmitter comparable to Earth's most powerful radars at distances of several hundred light years. It has found no confirmed technosignatures. This does not close the question. The parameter space is vast, but it does push the boundaries of what we can rule out further than they have ever been pushed before. And so we arrive at a picture that is both intellectually precise and emotionally difficult. The universe has given us an extraordinary abundance of planets. The biological chain from chemistry to civilization is long, contingent, and may fail at multiple points. Even a civilization that completes the entire biological sequence faces the separate challenges of survival, detectability, and temporal overlap with any potential observer. Each of these challenges further reduces the probability of contact. The cumulative effect is a galaxy that can produce planets by the billions, life perhaps by the millions, complex life perhaps by the thousands, and technological civilizations perhaps by the dozens, or the handful, or the one, spread across 13 billion years of cosmic history, almost never overlapping, almost never within range, almost never detectable. The silence is not a single mystery with a single answer. It is the compound result of many filters, many improbabilities, many separations in time and space, all working together to produce an outcome that feels, from our perspective, like emptiness. But the emptiness may be an illusion of scale. We are looking at a galaxy from inside a single moment, from a single location, with instruments that have been operating for less than a century, and we are surprised that we have heard nothing. Perhaps the surprise should be that we expected to hear anything at all. But what does this mean? What does it tell us about our place in the cosmos? About the value of what we are? about the significance of the silence itself? That is the question that remains. And the answer, when we look at it honestly, is more unsettling than most people are prepared for. Let us now stand back and look at the full chain, from beginning to end, and feel the weight of what it asks. A star forms from a collapsing cloud of gas and dust. Around it, a disk of leftover material coalesces into planets. One of those planets settles into an orbit at the right distance from the star. Not too close, not too far, where temperatures allow liquid water to persist on its surface. The planet has the right mass to hold an atmosphere. It has a magnetic field strong enough to shield its surface from the worst of the stellar radiation. It has the right chemical inventory: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, delivered by asteroids and comets during its early history. It cools. Oceans form. The raw ingredients of biology are present. That is step one, and it happens on billions of worlds across the galaxy. Now chemistry has to become biology. Non-living molecules have to arrange themselves into self-replicating systems capable of carrying and transmitting information. This step, abiogenesis, may be the hardest single transition in the entire chain. We do not know how likely it is. It happened on Earth within a few 100 million years of conditions becoming favorable, but we cannot extrapolate from a single example with any confidence. Recent work suggests the spontaneous assembly of biological information under plausible prebiotic conditions is far more improbable than previously assumed. This gate may be extraordinarily narrow. Suppose life does arise. For the next filter, that life has to become complex. On Earth, simple prokaryotic cells existed for approximately 2 billion years before the first eukaryotic cells appeared. Cells with a nucleus, with mitochondria, with the internal architecture needed to support larger, more energy-intensive organisms. This transition appears to have happened exactly once. 2 billion years of simple life, and then a single event, the engulfment of one cell by another, created the platform on which all subsequent complexity was built. Suppose the eukaryotic transition succeeds. Now, complex cells have to build multicellular organisms with differentiated tissues, specialized organs, nervous systems. On Earth, this took roughly another billion years. The boring billion. A geological eternity of single-celled eukaryotes before the first complex animals appeared in the Ediacaran period, and then radiated explosively during the Cambrian. Suppose multicellular complexity arises. Now, intelligence has to evolve. Not just the capacity to react to stimuli, which bacteria can do, but the capacity for abstract thought, for language, for cumulative culture, for understanding the world well enough to build instruments that extend beyond the reach of biological senses. On Earth, this required the contingent elimination of the dinosaurs by an asteroid 66 million years ago. An event that was not inevitable, not predictable, and not guaranteed to produce an outcome favorable to intelligence. Without that impact, mammals would almost certainly never have risen to dominance, and the cognitive lineage that produced us would never have existed. Suppose intelligence evolves. Now that intelligence has to develop technology. Not just tools, which many species use, but science, engineering, mathematics, the systematic investigation of nature, and the application of that understanding to build devices that can send signals across interstellar distances. On Earth, the gap between anatomically modern humans and radio technology was roughly 300,000 years. For most of that time, our species possessed the biological capacity for everything we have achieved. but the cultural and material conditions that enabled science and industry had not yet developed. Technology is not an automatic consequence of intelligence. It requires specific social, environmental, and historical conditions that may not arise on every world that produces intelligent beings. Suppose technology develops. Now the civilization has to survive. It has to avoid destroying itself through war, environmental collapse, resource exhaustion, pandemic, or risks we have not yet imagined. It has to maintain the social and institutional stability needed to keep operating complex technological systems across generations. It has to navigate the transition from a species that evolved for local survival to a species that manages planetary scale systems. On Earth, we have been attempting this for less than a century, and the outcome is far from certain. Suppose the civilization survives. Now it has to be detectable. Its signals have to be strong enough, persistent enough, and in a form that another civilization could recognize across interstellar distances. And as we discussed, civilizations may transition rapidly from loud, omnidirectional broadcasting to quiet, targeted communication, shrinking the detectable window to perhaps a century or two out of a history that could span millennia. Suppose the civilization is detectable. Now it has to overlap in time with someone who is listening. In a galaxy that is 13.6 billion years old, where civilizations may each last only a few centuries or millennia in their detectable phase, two civilizations have to exist at the same time and within range of each other. The probability of this overlap depends on how many civilizations arise and how long each one lasts. If either number is small, overlap becomes unlikely. If both are small, it becomes virtually impossible. And finally, suppose two civilizations do overlap in time. They still have to be close enough for signals to bridge the gap at detectable strength. The inverse square law guarantees that even powerful transmissions become vanishingly faint over thousands of light years. The effective range of detection for any realistic technology is a small fraction of the galaxy's diameter. This is the full chain: planet, chemistry, abiogenesis, complex cells, multicellularity, intelligence, technology, survival, detectability, temporal overlap, spatial proximity, signal strength. Every link has to hold. A break at any point produces the same result from our perspective: silence. And here is what makes this chain so devastating as an explanation for the quiet we observe. You do not need any single link to be impossible. You do not need a dramatic great filter that blocks everything. You only need each link to be somewhat improbable, and the multiplication takes care of the rest. If each of 10 steps has a 1 in 10 chance of succeeding, the probability of completing the full chain is not 1 in 10. It is 1 in 10 billion. Start with 100 billion potentially habitable planets in the galaxy. Run each one through a chain with those odds, and you end up with 10 civilizations spread across 13 billion years of galactic history. At any given moment, the chance that even one of them exists simultaneously with us, within detectable range, broadcasting in a way we can recognize, is small enough to explain the silence without invoking any single catastrophic barrier. The great filter in this view is not a wall. It is a series of gentle slopes, each one tilting the odds slightly further against the outcome we're looking for. No single slope is insurmountable, but the journey crosses many of them, and the cumulative gradient is steep enough that almost nothing reaches the summit. This is the answer that the evidence increasingly points toward. Not that the universe is hostile to life, not that planets are rare, not that some malevolent force is destroying civilizations before they can make contact, but that the full chain from habitable planet, detectable civilization is so long, so contingent, and so fragile at so many points that the final product, a technological civilization producing recognizable signals at the moment, another civilization happens to be listening, may be extraordinarily rare, possibly unique, possibly us. Now, what does this mean? The word alone carries a weight that we need to be careful with, because it can mean more than one thing. And the difference matters. One meaning of alone is absolute. We are the only life in the universe, the only planet where chemistry ever crossed the threshold into biology, the only world where anything lives, breathes, reproduces, evolves. If this is true, the implications are staggering. Every bacterium on Earth, every insect, every tree, every whale, every human being, all of it would represent the totality of life in the cosmos. A single fragile experiment running on one small rocky world, surrounded by an infinity of sterile emptiness. But this is probably not what the evidence suggests. The raw ingredients for life are everywhere. The chemistry that produces amino acids, the building blocks of proteins, occurs naturally in interstellar space, in meteorites, in the atmospheres of giant planets. The conditions for life's origin, liquid water, energy sources, the right elements, exist on many worlds and moons in our own solar system, let alone across the galaxy. It would be surprising if Earth were the only place where chemistry ever took the first step toward biology. Microbial life, simple and tenacious, may well exist elsewhere. Perhaps on Mars, in its ancient past, or in subsurface pockets today. Perhaps in the ocean beneath the ice shell of Europa or Enceladus. Perhaps on worlds we have not yet examined, orbiting stars we have not yet surveyed. The deeper and more likely meaning of alone is functional. We may not be the only life in the universe, but we may be the only technological civilization currently capable of looking for others. Not because intelligence is impossible elsewhere, but because the full chain from microbe to radio telescope is so improbable and so fragile that it almost never completes. The universe may be biologically active in scattered places, dotted with worlds where simple life clings to existence in hot springs and ocean vents and subsurface aquifers. But the distance between microbial life and a civilization that can send a message across the stars is so vast, and the number of things that have to go right along the way is so large that the galaxy may contain millions of living worlds and still be effectively silent. This distinction matters because it changes the texture of the loneliness. If we are absolutely alone, if nothing lives anywhere else, then the universe is a monument to emptiness and we are an impossible accident. But if the universe is scattered with life that never reaches complexity, if simple organisms exist on thousands of worlds, but no one ever builds a telescope or writes a symphony or asks a question, then the loneliness is different. It is the loneliness of being the only one who woke up. The only one who made it through every filter, passed every gate, and emerged on the other side with the capacity to look up and wonder. And there is a further possibility that is perhaps the most haunting of all. The galaxy may have produced other civilizations, perhaps dozens, perhaps hundreds, spread across its 13 billion year history. But each one may have risen and fallen in isolation, separated from the others by millions or billions of years, each one asking the same question into the same silence, each one concluding, as we may conclude, that it was alone. Not because no one else ever existed, but because no one else existed at the same time, in the same place, with the same capacity to listen. The loneliness of time is different from the loneliness of space. It is the knowledge that someone else may have stood where you are standing and looked at the same stars and heard the same silence and drawn the same terrible conclusion, and you will never know, because the universe did not arrange for your moments to overlap. We do not know which of these scenarios is true. We do not know whether we are absolutely alone, functionally alone, or temporally alone. The evidence is consistent with all three, and that uncertainty is itself part of the weight. But there is something else the silence tells us. Something that cuts closer to the question of what we are and what we owe to the improbability of our own existence. If the chain is as long and fragile as the evidence suggests, then what happened on Earth is not ordinary. It is not a routine outcome of planetary evolution. It is an event so improbable that it may have happened only a handful of times, or once, in the entire history of a galaxy containing hundreds of billions of stars. Every step in the chain, from the first self-replicating molecule to the first radio signal, required specific conditions, specific events, specific accidents of timing and chemistry and geology that did not have to occur. The asteroid that killed the dinosaurs did not have to strike. The merger of two cells that created eukaryotes did not have to happen. The particular sequence of environmental changes that enabled atmospheric oxygen, complex animals, primate intelligence, and human civilization was not a foregone conclusion. It was a path through an almost infinite forest of alternative histories, most of which led nowhere we would recognize. And we are standing at the end of that path. This is not a religious argument. It is not a claim that the universe was designed for us or that our existence serves some cosmic purpose. It is a statement about probability. The chain of events that produced us was extraordinarily unlikely, and the silence of the sky, the absence of anyone else who seems to have completed a similar chain, is consistent with that improbability being real. Not just a feature of our ignorance, but a feature of the universe itself. If this is true, and the silence increasingly suggests that it might be, then the question of whether the great filter lies in our past or in our future takes on a significance that extends beyond academic curiosity. If the hardest filters are behind us, if abiogenesis, or the eukaryotic transition, or the evolution of intelligence were the steps that almost never happen, then we have already passed through the narrowest part of the sieve. Our existence is the improbable part. What lies ahead, the challenge of surviving as a technological civilization for thousands or millions of years, may be difficult, but not fundamentally different from challenges that many civilizations could in principle meet. In this scenario, the silence is strangely reassuring. It tells us that the hard part is over, that the reason the galaxy is quiet is not that civilizations inevitably destroy themselves, but that civilizations almost never arise in the first place. We are rare because the biology was hard, not because the future is impossible. But if the hardest filters are ahead of us, if the steps we have not yet taken, long-term survival, stable governance across centuries, the management of technologies powerful enough to destroy us, are the ones that almost no civilization passes through, then the silence is a warning. It tells us that the galaxy may have produced many civilizations that got exactly as far as we have, and then failed. That the path from radio technology to long-term survival is littered with the ruins of species that couldn't manage the transition, and that we are approaching the filter that has stopped everyone else. We do not know which scenario is correct. The evidence does not clearly favor one over the other. The honest answer is that we are uncertain, and that uncertainty is uncomfortable, because the stakes are absolute. But uncertainty is not helplessness. The fact that we cannot determine where the great filter lies does not mean the question is meaningless. If anything, it gives the question urgency. Because if there is even a possibility that the hardest filter lies ahead of us, then the choices we make in the coming centuries about technology, about governance, about the management of existential risks, about how we treat the only planet we currently have, may determine whether the chain that produced us continues or ends. And here, finally, is the thought that the silence leaves us with. The most unsettling answer to the question of why we may be alone is not that the universe has no planets. It has billions. It is not that the universe is hostile to life. The chemistry of life is woven into the fabric of the cosmos. It is not that some single dramatic barrier prevents civilizations from arising. The barrier, if it exists, is not dramatic at all. It is quiet. It is cumulative. It is the gentle compounding of many modest improbabilities across a chain so long that almost nothing completes it. The universe may have countless worlds where water flows and organic molecules accumulate, and the conditions for life are met. And on some of those worlds, life may arise. And on a fraction of those, it may become complex. And on a fraction of those, intelligence may evolve. And on a fraction of those, technology may develop. And on a fraction of those, the civilization may survive long enough to send a signal. And on a fraction of those, the signal may be strong enough to detect. And on a fraction of those, someone may be listening at the right time. And the product of all those fractions, the final number, the count of civilizations that we could ever hope to detect, may be so small that the answer is indistinguishable from zero. That is not a dramatic conclusion. It is not a prophecy of doom or a declaration that the universe is empty. It is something more subtle and, in some ways, more profound. It is the recognition that the distance between possibility and reality, between a habitable planet and a detectable civilization, is so vast that the universe can be overflowing with potential and still nearly silent. The potential is real, the silence is also real, and the gap between them is the story of every filter, every bottleneck, every contingent event that had to go exactly right for anyone to be here to notice. And if you are hearing this, if you are a conscious being on a rocky planet orbiting a medium-sized star in the outer arm of an ordinary spiral galaxy, then the chain held for you. Every improbable step, from the first self-replicating molecule in a warm ocean 4 billion years ago to this moment, succeeded in sequence without breaking. The asteroid struck at the right time. The cells merged in the right way. The atmosphere oxygenated at the right pace. The ice ages came and went without sterilizing the surface. The extinction events were severe enough to open new ecological niches, but not so severe that they ended the experiment entirely. Intelligence evolved. Language developed. Science emerged. Technology was built. And here you are, a pattern of matter that has organized itself into something capable of contemplating its own improbability. The silence of the sky does not diminish that. If anything, it deepens it. Because the silence suggests that what happened here may not have happened elsewhere. That this particular chain of events, this specific and fragile sequence of transitions from chemistry to consciousness, may be one of the rarest phenomena in the observable universe. Not because the universe is small, it is unimaginably vast. Not because the ingredients are scarce. They are everywhere. But because the recipe is long, and the tolerances are tight, and the number of places where everything came together in the right order at the right time may be vanishingly small, we look up at the night sky and see silence. We listen with our most sensitive instruments and hear nothing. And the absence of an answer is itself an answer, not a definitive one, not a final one, but an answer that tells us something important about the nature of what we are. We are not the inevitable product of a universe that was always going to produce us. We are the improbable product of a chain of events that almost never completes. And the silence around us, that vast, humbling, terrifying quiet, is the sound of all the worlds where the chain broke, all the planets where life never started, all the oceans where cells never merged, all the forests where no creature ever looked up, all the civilizations that may have flickered into existence and then gone dark, too far away, too long ago, too brief to ever reach across the void and say, "We are here." The silence does not prove we are alone. It may never prove that, but it reveals, with a clarity that grows sharper with every null result, with every survey that returns nothing, with every telescope that finds another world and no signal from its surface, how fragile it is to become something that can ask the question at all. And perhaps that is the thought worth carrying away from all of this. Not despair at the emptiness, not triumph at our uniqueness, but a quiet, honest reckoning with the improbability of our own existence, and the recognition that if the chain is as fragile as the silence suggests, then what we have, this brief moment of consciousness in a vast and possibly empty cosmos, is not something to be taken for granted. It is something that was never guaranteed, something that almost did not happen, something that, as far as we can tell, may be happening nowhere else. The stars are out there, hundreds of billions of them in this galaxy alone, many of them with planets, many of those planets with the right conditions, and from all of them, from every direction, at every frequency, across every moment we have listened, the answer has been the same: silence. Not because the universe is small, but because the chain is long, and what we are, what it took to get here, what it means to be a species capable of hearing the silence and understanding why it is silent, may be the rarest thing the cosmos has ever produced. Good night.